Show my UChicago mug.
I'm sharing the screen. My screen is shared. We're recording. Closed captioning is turned on. Welcome, everybody, to the Fast Code seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the seminar, and I lead community outreach for the larger Fast Code project, of which the seminar is a part. And before Julian introduces our speakers, I'd like to take just a minute to let you know about the Fast Code seminar and the larger Fast Code project. I put the link to the Fast Code website into the chat. I can put it in one more time if you just got here. And it's on my screen as well. This is a community about making software performance engineering broadly accessible and strong as its own field. And so we work on research and education and technology and skill building. Lots of activities, including one of our featured events is, of course, this seminar. And if you look at the seminar, you'll see that there's today's event here. We'll be recording and posting that, and lots of other seminars in the past. Many thanks to the organizing committee, Kuba and Roberto, Christian, Julian, and Yihan. You might have noticed if you were looking closely, don't have a scheduled seminar for next month or the month after. So if you have a nomination, please reach out to me or Julian or anyone on the organizing committee. And I want to mention just one thing before I turn it over to Julian in terms of all the ways you can get involved, which is a shout out to our instructors community. We have had a lot of effort put into making it easier to teach performance engineering. And so if that's something that you care about, we've got a group of people who are actively working on the future of teaching software performance engineering, whether you call it that or work it into a class about something else. So if that's of interest to you, I encourage you to take a look at our instructors community and let me know about any way that we could get you involved. That's what I have to say. I'm going to turn it over to Julian to introduce our speakers.
All right. Thanks, Bruce. So I'm very happy to have Andrew Chien and David Gleich as our speaker for today's Fast Code seminar. Andrew's a professor at University of Chicago and also a senior scientist at Argonne National Labs. He's led the Zero Carbon Cloud Project since 2015 and is known for research on data centers, renewable energy, sustainability, cloud resource management, software and large-scale system architecture, and also graph computing. And he's the leader of the UpDown system project for designing graph analytic systems, and that's the topic for today's seminar. Andrew's received a lot of awards for his work. He's also a fellow of the ACM, IEEE, and AAS. And he's received his degrees all from MIT. David Gleich's a professor at Purdue. His research focuses on algorithms for network science, graph algorithms, numerical linear algebra, and scientific computing. He's also received a lot of awards for his work, including the Sloan Research Fellowship and the SIAM Outstanding Paper Prize. And David received his degrees from his master's and PhD from Stanford and his bachelor's from Harvard Med. Great, so I'll turn it over to the two of you, Andrew and David.
Great. Thank you so much, Julian, and thank you, Bruce. It's a pleasure to be here. Let me just jump right in because we don't have that much time. Let's see, how do I advance here? Okay. Today we're going to talk about a bunch of things. The motivation for the UpDown project, which is a 4-year running IARPA-funded project, is to deliver scalable high performance. I'm sure something that many people here are interested in. And the way we've approached the problem is to try and build high performance accelerators that are not high Q. And I'll explain what I mean by that in a minute. We'll talk about the UpDown approach to both programmability and control of the hardware. And then David will talk a bit about what UpDown enables in terms of how to think about programming. And then we're very excited to be able to tell you that we're actually trying to build the UpDown machine. So we'll tell you a little bit about where we are with hardware and software status and plans. So the inspiration for this talk really comes from this wonderful paper that was written by Charles and several colleagues at MIT called "There's Plenty of Room at the Top, What Will Drive Computer Performance After Moore's Law." About 6 years ago now, that paper was published. But the idea was that Feynman had posited 70 years ago, 75 years ago, that microelectronics miniaturization was going to be a major driver for computing performance. That has largely been realized, but petered out in recent times with the end of Dennard scaling and the end of Moore's Law. So this paper calls out this idea that top of stack innovation, meaning software algorithms and architecture, really had to become drivers for computer performance in the coming decades. The problem that we've been seeing is that lots of the architecture innovation that's been happening has been narrow customization. And we see it in the AI world, we see it in the media processing world, we see it in crypto world, and so on and so forth. And that narrow architecture design, while it gives performance for perhaps an application, perhaps a domain, really hampers and limits software and algorithm innovation for higher level kinds of top of stack innovation, and therefore is impeding actually software. So we have this analogy that we try to use. I was trained as an electrical engineer, and when you're an electrical engineer, they teach you about things like filters. And a high Q filter is something that produces a really, really high selectivity, right? So as this picture shows at the left here, a high Q filter as a function of frequency, like a bandpass filter, might have a really, really high amplitude to pass through the filter for a very, very narrow thing. So the high Q refers to the narrowness of this peak, right? And therefore the selectivity. If you think of a computer system as a high Q filter, you can think of taking applications and programs and data structures and actually implementations of programs, and you pass them through the hardware. And if it's high Q, then maybe if your program is shaped just right, it uses the cores in just the right way, if it uses the memory hierarchy in just the right way, everything is perfectly balanced, then you can get good performance. But if you somehow don't match in some important dimension, then you get bad performance, bad performance, bad performance. In some sense, the practice of software performance engineering that Bruce spoke about is this idea of how do you, shift the performance to elicit the good performance from the system. So if you take this analogy of software behavior, filter, 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 resulting performance is a way to think about, both software tools and architecture. And you can think of this as a generalization of Sam Madden's, idea of roof lines, which I'm sure you've talked about in this group. If you have this kind of view of the world, then most of today's accelerators are high Q systems, and you must pass multiple high Q filters in order to achieve performance on the system. What are some examples of that? Well, on a CPU, right, you take your program, and one of the first order things, a multi-core CPU, you have some parallelism, but you have to have lots and lots of data reuse. Otherwise, you won't get high performance. What about another common accelerator? A GPU. You take your program, you better have lots of fine-grained data parallelism, and it had better be regular data parallelism because that's what the GPU can do. You better have regular control so you don't have thread divergence. Like I said, you better have regular data parallelism because you got to have memory coalescing work and so on. And then nowadays, GPUs even have caches, so you have to have lots of data reuse. And then now if you're going to make performance out of tensor cores, you need to use dense matrix operations, small ones, at least, and break up your computation and align it to really get high performance. If you're a fan of TPUs, in TPUs, maybe you have different constraints. Maybe you have a huge pressure to create large dense matrix operations in order to get performance. And this has other forms, right, in other areas, like I mentioned, media accelerators. Most media accelerators have fixed or a small set of data types and data parallelism across those data types, and in some cases, fixed algorithms. So these are all examples of high Q filters that are realized in accelerators or customized hardware And they really narrow the space of what's possible with software and the ability to innovate above. So the impact of these high Q structures on software and algorithms, these high Q structures in architecture, is that if you take stock programs off of your desktop or something like that, is that existing programs don't run well. You need new software. That's why we have now a cottage industry of folks being trained to use and write CUDA or SQL or whatever other favorite thing you do. And that's because many algorithms and data structures that are classically good, right, in the theoretical frameworks and in the classical theory we've been taught, don't work well in these frameworks. So if you have hierarchical parallelism or regular parallelism, you might not be well suited to GPUs or even CPUs. If you have heavily conditional control, irregular memory access, like you see in graph computations, we're going to talk about a lot, or low data reuse, you're going to see bad performance. If you have interesting data movement, right, pointer indirection, jumping back and forth, traversing the memory, in reverse address order or something like that, you're not going to match the prefetcher, and you're going to get really, probably bad performance from the memory hierarchies and so on. Or you could fundamentally not match the machine. You could have hardwired specific formats. Like now we have this proliferation of numerical formats. If you don't like any of those and you want something different, you always have had kind of a bad time. So a lot of work goes in to restructuring computation to match the idiosyncrasies of the machine, and that causes program complexity. Now, of course, some of this is intrinsic. Software performance engineering has been with us forever, but it's increasingly bad, and it's being exacerbated by the complexity of these accelerators. But maybe more important than that is that in some sense, what it does is it fractures the software base and it destroys software portability. So you wind up with software that's tuned for just one platform's queue, not in a general sense. So you now have an inability to share that effort for tuning. And so one way to think about this as a major concern is this become the death of general purpose portable software, something that has revolutionized the computing world in the last 30 years, maybe, is seeing it's being challenged by these high Q systems. So could we have an accelerator that could support top of stack innovation? The idea here is the picture on the left is the high Q system. Our dream is to have a system that, of course, is high performance, right? So lower, but lower Q, meaning the difference between the peak and the other levels of high performance is much smaller, right? So this allows software innovation and algorithm innovation to happen on top of this, on this higher level of performance, but also to bring us to another level of performance by adding sophisticated software and algorithms and so on, not being forced down into just a simple single restricted model of the architecture. And that is the dream of the UpDown project. And I would argue that's a better architecture performance profile than the super high Q systems we see on the left. So let me just jump into this. So the UpDown approach is to create a model in which you can orthogonalize to a large degree program development. And this is about parallel program development, which has long been super challenging, both at the multi-core level, but also at the scale out supercomputer or cloud kind of level. And the UpDown approach allows us to orthogonalize three different things. First, the expression of the computation structure, what we think of as the compute structure, that would be the expression of the parallelism and the decomposition of the work into parallel tasks and so on. The second thing that we allow you to do is to take that computation structure and map it in a flexible way to compute locations. So the structure of the computation, when it's expressed, does not implicitly include a mapping. The mapping can be done separately, right? And that allows you to deal with things like load balance and all of those kinds of things in a flexible way. In addition, the computation happens relative to a global address space, and therefore we have global data structures that can be uniformly accessed, just like you assume you can in a multi-core processor, but seems to have fallen by the wayside in lots of these large-scale parallel systems. And the UpDown programmers have a separate way of controlling data structures and layout and distribution across the distributed memory system. So the idea here is that if you can orthogonalize these three aspects of program development, then I can very flexibly explore the space in order to reach high performance without having to do lots of gratuitous rewriting of code and changing of structures and so on in order to do those experiments. So that's the dream. Let's just talk about a few key aspects of the UpDown programming view. The UpDown allows you to have fine-grained MIMD parallelism, and it has hardware structures that support it as inexpensive fine-grained tasks. So that allows programmers to expose vertex and edge parallelism in graph applications directly. And so we are able to express massive irregular data parallelism. We need about 3 billion-fold parallelism to fill the largest machine. And it turns out if you exploit vertex and edge parallelism directly, you only need a graph of, maybe 100 million vertices, maybe a billion vertices, and a few tens of billions of edges to actually scale to a very, very large machine, to 16,000 nodes. We have provided a hardware-supported global address space to enable that flexible software expression I described before. And then the system fundamentally has plentiful memory bandwidth and system bandwidth. And it's primarily a cashless system. It has scratch pads. I'll talk about that later. But the fact that you have plentiful memory bandwidth actually is something that makes programming much, much simpler and makes the system much lower Q. And then finally, UpDown is a dynamic parallelism model, which makes it easy to create parallelism in response to local data structure or local control structure, not an SPMD kind of programming model or a SMPTE kind of programming model, where you have to laboriously pack together, right, any kind of dynamic or regular parallelism into regular structures. In UpDown, each individual message send will create a new task or a new thread logically, exposing fine-grained parallelism in a very natural way.
Andrew, I have a clarifying question.
Sure, please.
A couple slides ago, you summed up the orthogonalization by saying, now I can explore the space.
Yep.
And in the vision of UpDown, who or what is the I that is exploring the space?
Well, it could be a human today. It could be a auto tuner. It could be an AI in the future, right? So, yeah, we don't have any particular assumption about what that is. The main thing is to reduce the friction in exploring the space, right? So you don't have to rewrite massive amounts of code. You don't have to reorganize the structure of the application in order to explore this space. That's what the orthogonalization is intended to allow you to do.
Thank you.
Make sense? Okay.
Yep.
So I got to go fast here so David gets his time, but let me just dive down and talk about what the magic at the architectural level is. What UpDown is it's a collection of very, very simple lanes or cores, depending on what you want to call them. And down at the heart of it, you have a traditional execution pipeline. But what's all around the core is now completely different. So we have special hardware that schedules event-driven execution on this core, and it supports multiple register thread contexts, right, in order to allow a latency tolerance. So the hardware is all designed to allow events or threads to be scheduled in a single cycle, which supports the very, very fine-grained execution. We can create, schedule, or destroy a thread in a single cycle. The multiple register contexts provide 128 threads, so we can have many, many threads to fill the pipeline. And we have special instruction set support for efficient short threads. I'll talk about short threads in a minute. But as important, we have a way to construct scalable high memory parallelism. So the software supports explicit control of split transaction operations to the DRAM, which allows a single thread to have many, many outstanding requests, sort of as many as it wants, and allows a single core to move up to 22 gigabytes per second. A single group of these, we call it an accelerator, 64 of these, can move 1.4 terabytes per second, HBM3E kinds of speeds. And what we call a node in the UpDown system is 2048 of these. I'll get to that in just a minute. But it's 2048 of these very, very powerful 2 billion instructions per second computer pipelines. The surprising thing is when you put together a pipeline like this with this kind of stuff around it, it might sound like it's very complicated, but the size of our cores is more like the size of a single in-order RISC-V core than it is these gigantic, complicated out-of-order cores you see today in mainstream multi-core systems. So that means you can have many more of them. So in a single node, you can have, as I said, 2048 of these parallel, event-driven kinds of lanes. We combine that with a traditional kind of CPU, which has a memory hierarchy and a traditional multi-core structure. So the accelerator focuses on the computations that have low data reuse. And then we combine these together into groups of these lanes around HBM stacks. And then in a single node, there's 8 of these HBM stacks with 4 of these accelerators clustered around each of the HBM stacks, giving 32 of those accelerators and 2048 lanes overall. That's a lot of hardware detail. The conceptual programming performance model is really kind of simple. You want to think of it as having a whole bunch of threads, maybe 10,000 threads, 20,000 threads above a global flat memory with no caches and with lots of memory bandwidth. That's the conceptual programming model. That system, the reason that it works is that each of these threads can be various sizes. Here's a bunch of histograms of different applications and different thread sizes, page rank, triangle count, Jacquard similarity, partial match, and so on. The main thing to notice from these histograms, I know it's a lot of detail, is that the axis is a very, very small number of instructions. This is the number of instructions executed per activation of the thread. And you can see for some of these applications, they're all less than, say, 75, all less than 50, all less than 150 or 200, which is dramatically lower than what you see in a conventional system where you would typically schedule 1 million or 1 billion instructions before you actually switch threads, at the system level. The hardware that I showed you takes these threads and these thread invocations and schedules them one after another on these cores. And you can see like it schedules this blue thread, then this yellow thread, then this green thread, and then another event comes in and it comes back to this blue thread and so on. And the interleaving or the combination of these many threads allows us to achieve really high core performance. So this fine-grained parallelism is then being multiplexed very efficiently onto this hardware. And the net benefit of that is we get dramatically higher lane utilization and therefore performance from this kind of hardware. So what's shown on the left here is data on core utilization. Think of this as the number of the issue slots in the instruction pipeline that are utilized. On the left, a traditional multi-core processor running graph 0 graph library with 20 hardware threads. And then 2 examples of parallelization of the same algorithm, the triangle counting algorithm, on UpDown. You can see that we're able to get upwards of 90 to 95% core or lane utilization, whereas typical for these kinds of applications, as you scale out in multi-core, is 10, 15% kinds of core utilization. And we see similar kinds of core utilizations on optimized GPU libraries as well. The combination of much, much higher efficiency, so this gives you 5 to 10x, depending on what your baseline is, the utilization, and the fact that these cores are simpler means that at the node level, with similar silicon area, we're able to get dramatically higher performance. So this is the performance in gigatops scaled for the same kind of node area that we're able to deploy in a multi-core processor versus one of these UpDown accelerators. And the way that we describe this is we're able to get about 50 times higher performance with 1/3 the area compared to a multi-core processor. So if you talk about at the node level, we might be at 150 times the performance on these kinds of irregular graph algorithms. So we try to distill this down into a bunch of different algorithm comparisons. This is a broad comparison where we tried to build all of the libraries that are present in the cuGraph library. And this is a comparison of performance on the K-truss algorithm, which if you know the algorithms, this is a triangle counting computation combined with per edge attribution of the triangles, right? So you keep account for each of the edges for how many triangles it participates in. Those of you who think about these kinds of systems will think of this as a triangle count fused to a GUPS operation, right? Where you have to do an atomic GUPS kind of operation. So this study that we did shows that you can achieve the performance in a single node to be comparable to 1,000 times that of a traditional multi-core system. This is a pretty big 128 thread multi-core system, and as much as 40 times faster than an H200 GPU. Now we've done these studies for a whole bunch of key graph algorithms, Louvain, connected components, strongly connected components, PageRank, BFS, K-cores, ... And the performance benefits are routinely more than 100 times compared to CPUs. And compared to the H200 GPU, we see anything from 10x to maybe 60x. The interesting thing is that the performance gap seems to increase the more complex the algorithm. We think a reflection of the difficulty of programming the SMPTE architecture and matching these more complex algorithms to the underlying regular structure of the GPU hardware. We were very pleased that this study won an MIT Graph Challenge Innovation Award. at HPEC just last year. And I should note that these performance differences are this large, even though the graphs we're computing on are relatively small. So this data is taken from the SIT patents graph from the Stanford SNAP collection, and it's highly skewed, of course. It's a social network style graph, and it's only about 16 million edges. So we're achieving very, very strong scaling, right, and good performance. This is a bunch of speed ups for the collection of algorithms I mentioned earlier. I won't spend much time talking through them, but you can see that, for the ones that, there's a lower speed up, we can see as low as maybe 10-fold speed up. But for some of the more complicated ones like Louvain or K-Trust, we're seeing, 40+ fold speed up with the geomean of something like high 20s, maybe 30, right? And we continue to explore more of these. Another interesting note that David will speak to later is that this is at a significant power advantage. This system is much lower power than the H200. Okay, I see I need to speed up a little bit, right, David? Help me out here. I should try and finish in the next 5 minutes and then pass to David. So the system scales. This technology can be deployed in single card, 8U server racks, and so on. When we finish the hardware, we don't have up the hardware quite yet. For IARPA, we designed a very, very large scale version of this, 16,000 node system with 2,048 lanes per node, which gets you to 33 million lanes or cores overall. So a 33 million physical parallelism machine. And David will talk about some of the kinds of speedups we're able to demonstrate on that, again, with relatively small graphs. How do you actually think about programming the UpDown system? This is a performance programming kind of class. Let's talk about what it actually looks like. The way you think about it is you first try to expose lots of data parallelism naturally. In graph, this is relatively easy, right? The classical way to write down in a graph theory or algorithms class is in operations of sets of vertices and edges. You do all across the edges, do all across this set of vertices. And you can express this really naturally with these really cheap threads. You don't need to worry much about locality because memory bandwidth is plentiful, provided you have enough parallelism. And then, of course, because these graphs are highly skewed, you have to load balance it, right? So that's a critical thing to getting good speed up. And the surprising thing is the machine is so efficient with fine-grained tasks that we discovered that simple, fast divide and conquer techniques work. You can do a recursive partitioning on the fly and scale to very, very, very large machines with high efficiency because the machine is so efficient. The data use doesn't have much inertia because we have so much memory bandwidth. So we don't need very complex stateful migration systems like Silk, wonderful work in NUMA multicores and so on. But we don't need that kind of stuff. And the finer grained parallelism, the better. You saw that we can execute all the way down to sort of 10 instruction kinds of invocations and be efficient. So this is, I showed you these graphs earlier, and this is the distributions of the fine-grained threads. We are literally getting extremely good hardware efficiency with thread invocations of these sizes, like 150 instructions. I mean, you can barely say hello in most programming systems with 150 instructions. And literally millions and billions of thread activations of these sizes are being combined together to create that super high performance and utilization. So the key that enables all this is the UpDown hardware can efficiently support these fine-grained threads. Why is it important to support fine-grained threads? Well, here's an example of how it makes a difference for scaling, say, the triangle counting application. Here we were running on a scale 25 graph, so maybe 30 million vertices and 500 million edges. The machine scale here is 1 to 512 nodes. If you remember, I said 2,000 lanes per node, so this is actually 1 million lanes at this side of this graph. And what you can see is if you do a coarse grain, what we call a coarse grain partition, right, where you take vertices and you map them out to these lanes, right, you run out of parallelism around 16 nodes, right? And the loss in performance that you can achieve, increases steadily out to 24-fold by the time you're out to 1 million lanes. right? Because you have to keep in mind that at 16,000, 16 nodes, you're already at 32,000 physical parallelism, 2,000 lanes per node. But if you're able to do fine-grained parallelization and work distribution, that is per vertex pair for the triangle counting kind of comparisons, then you can scale even on this relatively small graph of a few hundred million edges and tens of millions of vertices out to millionfold parallelism and get beautiful, nearly linear scaling all the way out to 512 nodes or a millionfold physical parallelism. So the machine is capable of parallelizing very, 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 very thin amounts of work. And we talk about, trying to stay above like maybe 100 or 50 vertices per lane in order to keep the machine scaling properly. In the case of triangle counting, it's a little bit compute heavy. So out at a million vertices, right? Out at a million physical parallelism, we only have 30 vertices per lane actually, and we're still achieving super good linear scaling kind of performance. So we were able to achieve quite strong scaling. So how do you program this? Well, you have to do two things in order to program this machine, and we think it applies to far more than graph, but it's really easy to explain for graph. The first is you create these little event-driven kernels, and then you use a very flexible MapReduce framework to coordinate the massive parallelism that's been exposed. So in order to create these kernels, we have an event-driven language called UDWeave. Think of it as like an actor language, if you know about actor languages, or think of it as like a React, right? So JavaScript React is really an event-driven framework used for programming user interfaces. And UpDown's UDWeave actually exposes our event-driven features in the UpDown machine. So programs at this level look something like this. They'll have some shared state, right? Think of this as the object state. They'll have some, what you might think of as member functions if you're an object-oriented programmer, but these are actually events. And those events do various things like initialize the state, send messages off to the memory, and respond to events coming back. This is a super simple program example. And what it does is it prefetches data and brings it into the local scratchpad. So the start event, just ignore this boilerplate here, has a loop which sends to the DRAM, right, requests of various sizes, right, for blocks of memory to come back. And this loop you can see is all asynchronous operations, and this allows a UDWeave program to create large amounts of memory parallelism because that loop can be shoot all these requests off, and then this program deschedules itself at the end of this event. Those memory requests actually are tagged with a continuation called write_lm. When those messages come back from the memory, they actually trigger this event here, and this event then takes the memory and puts it into some local location, and then counts how many requests have come back, right? And then when the right number of requests have come back, then it triggers that it has completed its work and completes that bookkeeping task. So this simple example shows how the event-driven mechanism works and shows that you can actually interact asynchronously with memory. And magically, all of this stuff is like single cycle operations. So none of, even though it says send, I know that's scary for people. They think that's thousands or tens of thousands of cycles. No, that's one cycle in our machine and really can be executed very efficiently. So if you imagine having a bunch of kernels like this, then we have a MapReduce framework that allows you to compose them together. And that MapReduce framework you can think of as you write your map function in UDWeave, and you can write a reduce function in UDWeave, and do the normal map shuffle reduce kind of computation. So it's easy to specify and control a massive amount of logical parallelism across arrays, hash tables, graph abstractions, and so on. Because we're dealing with graphs or data parallelism, we have easy expression of million and billion-fold vertices and edges. And remember, each of these tasks is an event-driven, independent control flow function like I described to you earlier. So it's super easy and flexible. You're not restricted to SIMD or SIMT or anything like that. It's very, very flexible parallelism. Let me see. How many more slides do I have, David, before I need to hand to you? I need to finish here.
So 3 or 4. You might want to skip the PGA stuff if you're looking to save time.
I'll do that. I'll do that. Yeah. So how general is this? This MapReduce thing can be done over traditional arrays for the index space of the array. And we have something called a scalable hash table, super useful in graphs, where you can take and hash that index space and then put data into buckets, and you can do alls over sets of elements in the hash tables. And then we actually, because all of this is programmable, we don't have to use a fixed hash function. The programmer can actually customize the key to bucket mapping, and the programmer can do explicit tuning based on application for load balancing of their regular data. And of course, all this stuff is spread across the machine. All of this can be expressed in the same MapReduce framework over these different kinds of underlying data structures. An example of how the flexibility of UpDown actually is enabling algorithm and data structure innovation. Okay, I'm going to skip the PGA stuff per David's advice. So the idea here is that UpDown is going to enable this low Q property because it enables software control of many of the key parameters that are fixed in other hardware architectures, and therefore, software has to conform to rather than control. So let me just list 3 of these things, and then I'm going to hand off to David. Oh, I'm sorry, one more slide. Low Q actually works. Breadth first search is one example of where we already have very, very complex and sophisticated algorithms. Then you can see that you can use a push BFS algorithm, a push pull BFS algorithm, or a proactively load balance push algorithm for BFS. And we can still see extremely good scaling across all of these. We see differences of 2 to 4 for these vastly different algorithms, not 100-fold like you might see on a high Q accelerator. So what are the kinds of things you can control in UpDown that you can't control in conventional architecture? The threads are scheduled under software control. You saw in UDWeave, there's an operation called yield or yield terminate. That allows software to decide what's a short and a long latency operation, what's an unpredictable latency operation, and therefore schedule around those things, right? Like making sure to issue all the long latency requests before you deschedule and then only get woken up when those things come back. So that allows the software to manage the execution pipeline very efficiently, supported by this underlying one-cycle hardware. Software can actually also control the memory parallelism. If you've ever tried to do this in a conventional architecture, it's practically impossible because there's some underlying physical structures that actually define how much memory parallelism there can be, right? In UpDown, you can actually have unlimited memory parallelism. Yes, I said that right, unlimited memory parallelism. And we wrote a paper with that title. And that's because the software can explicitly describe split transaction memory operations and express all of that parallelism to the memory. In addition, it can also describe the size of data transfers. You can load 1 word, 2 words, 3 words, 4 words, 5, 6, 6, all the way up to 8 words in chunks with various alignments. And the hardware will just do it for you. So the software can decide, actually, I don't need those 3 words, I just need these 2, and get them very, very efficiently. And then finally, for the scale out situations, the software can manage actually the global data distribution. It's not subject to some OS controlled management policy. So with that, I'm going to give the remaining time to my colleague, David.
All right, awesome. So as Andrew has talked through this, we have loads of examples of UpDown programs that scale up to the massive systems that IARPA has, and also scale down to lots of smaller runs as well. So I'm just going to talk through a couple of them and explain a little bit more about what goes into programming some of these things, and also some of the opportunities. So Andrew, if we can go to the next slide, I think that's probably the best way to do this. So here's an example with triangle counting. What does the triangle counting application that we build actually look like in terms of some of the primitives that Andrew has introduced already? So we briefly covered this idea of MapReduce, which we call key value map shuffle reduce, just to sort of introduce all the different pieces of it. We've got a key space, a value space, and we're doing some map shuffle and reduce steps. But of course, we don't have to run the shuffle and reduce steps if we don't need them for particular steps. So for something like triangle counting, we have an input set of just an edge list. And the first thing we do is we put that into one of those scalable hash tables, which actually gets combined into that parallel graph extraction we didn't quite have time to go through. But it's just a simple sort of like vertex aligns edge store where you can iterate over edges or vertices. So very similar to many other types of graph data structures. Once we have that, we do a MapReduce step to compute degrees. The next step in triangle counting is you want to essentially orient each edge so that you're doing it like you are only finding every triangle in one orientation. So then we do that with another map reduce step to essentially go through and strip out edges we don't need. We're going to do just simple intersections between these. And so that's going to be done by sorting all the neighbor lists. So we essentially run a whole bunch of different map reduce steps for the high degree vertices, and then just do local sorts on the low degree vertices. So a little bit of split, like different types of parallelism for high versus low degree there. And then we essentially either parallelize over vertices directly, which was that coarse algorithm that Andrew had said. So a vertex considers all of its edges and then finds all the triangles by doing intersections over all of its edges. Or we do it on edge pairs, or sorry, the vertex pairs in the edges. And that just runs a simple reduce. We recognize that binary search is in principle faster, but just a simple reduce. Sorry, a simple linear intersection algorithm turned out to be better in our experiments here. So again, these algorithms are pretty conventional. And so the neat thing about running these types of algorithms is that there's all sorts of things that you don't have to think about as a programmer of these. You don't have to think about graph partitioning. So the design of UpDown is very much a flat memory structure. So you get really reasonable performance if you access it on your own node or if you access it on a remote node. The system is designed to be latency tolerant. We don't have to think about the network topology at all. There's a big, the vision for IARPA and some of the local machines is just with a big expander network there that can support basically everyone communicating with everyone else at the same time. You don't have to think about local versus global IDs, which is something that comes up a lot in distributed programming. You just have a single shared either pointer or offset ID that you can share anywhere around the network with any particular compute thread, and they can all access the same data. You don't have to think about any type of alignment or prefetching or anything like that. As Andrew pointed out, we have effectively unlimited memory parallelism. So next slide. So again, just with something like breadth first search, we do the same type of algorithm. So at breadth first search, what we're doing is we're basically propagating frontiers through the graph. Each of these frontier propagation steps is done with a map reduce step. And the reduce step here ends up generally being a no-op because we essentially just write directly into memory. So we don't have to do any type of complicated shuffle to ensure that we're only writing once. And just in the interest of time, let's go on to the next one. So when we were investigating this for IARPA, they always wanted to know how this is going to compare to sort of the state-of-the-art big machines out there. And so they wanted us to do projections up to massive RMAT graphs. And so we worked with them a lot on a way of taking measurements that we had done on all the systems we were able to simulate and figuring out how well they would run on graphs that we can't simulate. And essentially, the system scales up with as much system power as you want to throw at it. So if you want to throw 20 megawatts of compute power, I think that's megawatts in the like in the axis there, not kilowatts. Like some of the Fugaku systems, we would anticipate doing many orders of magnitude more than they do. And also, we haven't really done any software tweaking yet on our algorithm. So we anticipate that, you know, if we sat down for a couple weeks, like a month or two, we would probably be able to squeeze out at least another factor of 2. For instance, we're not doing this tree optimization that a lot of the modern Graph 500 runs are doing. Next slide. So one of the pitches with this, there's plenty of room at the top, is that, of course, you can sometimes run better algorithms. And sort of all else being equal, an algorithm that does less work, like assuming all parallelization is equal, is just going to be faster and higher performance. And so one place we looked at this was in terms of PageRank. So there's this algorithm called data-driven PageRank. And we don't have time to go into a ton of detail on it, but let me just try and cover it in a couple of bullet points here. PageRank is this iterative algorithm where essentially the value at my node depends on the value at all of the other nodes nearby me. And essentially nodes are exchanging messages, and you can show that a variety of things converge. So essentially I look at all the nodes connected to me and update my value based on them. And as we go through cycles of this, everyone will converge. Now, the trick here is that at some point you start making small changes to a vertex value. And the idea with data-driven PageRank is at some point your changes are so small you might as well not make them. And so what we do here is we say, okay, you want to converge to a particular tolerance. Then if your change is less than your tolerance, you don't accept it anymore. You say, okay, my neighbors told me I should have a new value, but that's smaller than the tolerance that I'm looking for. Like the change to my value is smaller than my tolerance. So I'm not going to actually accept that value and take that as an update, which means that then the neighbors of that node don't have to do any updates that are caused by you. And so you can I mean, this sounds heuristic and hacky, but you can formalize this into a rigorous algorithm that satisfies a convergence guarantee and everything like that. And so if we're able to do that, let's go to the next slide there. Essentially, we're able to formalize that into an algorithm that uses these primitives again. So it's an algorithm that's designed to save work, but most of the changes don't happen in the first two iterations of PageRank. So what our implementation does is it runs 2 iterations of PageRank, and then it basically maintains a bit mask over vertices, which is the ones that have changed enough. And so then when we're doing our update over everyone, we look at this bit mask and we say, oh, okay, did I update enough to change? If not, then I don't have to do my update. But if either I updated enough or one of my neighbors updated enough, then I do have to update this. And so this, again, still uses that same MapReduce infrastructure. It just checks if I actually need to update myself beforehand. And this allows us, so when we measure this, we're actually doing less work. So when we're reporting these numbers, these are in giga traversed edges per second, but just think of this as how many billion edges per second we're able to do as a function of how many nodes in the system. So we have one node over here, and we can see sort of linear scaling would be, we add more nodes, we go faster. The key point here is when we introduce this data-driven thing, we measure this in terms of effective. We say, how many edges would you have had to do to sort of converge in the other scheme? And we treat that as effectively running faster, just so we are on the same axis here. And so we can get factors of 4 to 2 from these sort of algorithms on top of all of the other architecture. I mean, like on top of going fast already. All right. So I'm gonna probably have to skip through one of these other things. So Andrew, I'm going to go through this really quickly. So one of the things we did was a year or so ago, we said, well, how general can we make these libraries on UpDown? And so essentially we wanted to do a load balanced study on this graph benchmark suite. So if we go to the next one, the reason we need to do this load balancing is something we've tucked a little bit under the rug. So some of the previous studies, we essentially used a very primitive form of load balancing on these graphs where we would do vertex splitting. So if you had a very high degree vertex, we would oftentimes partition it up into some fixed size regions and then do a little bit of software coalescing after the fact. But we wanted to see if we could get away with like a zero pre-processing style approach here. And this is needed because a lot of these graphs, as you folks know, and Andrew alluded to before, have very highly skewed degree distributions where there are nodes with degrees of, say, 1 million, even though the average degree is something like 10. And so that huge imbalance causes a problem. And so essentially we set out to port most of the GBBS primitives and things like an edge map where we can do auto load balancing through these. And so like again, the GBBS is a really nice suite that sort of exercises a lot of algorithms with a couple of common primitives and has been shown to scale really well on multicolor systems. We wanted to take all these essentially optimal algorithms and see how well we can do on the scale out or distributed up-down systems. So if we go to the next slide, the approach is going to be really simple here. We're going to essentially distribute the work across lanes so that each lane has an approximately equal amount of work. And for things like an edge map, we're going to use the number of edges sort of essentially to estimate the work that you need to do per vertex. And then we're just going to divide the work recursively. So the way that works, next slide, is we're going to start with something like a graph in CSR form and just recursively split the work in such that we have about half of the work in one half of the compute infrastructure and a half of the work in the other half of the compute infrastructure. And you might think, oh, aren't you going to spend a lot of time sort of doing this and then doing it recursively? And the answer is no. So if we go on to the next slide, the cost of splitting here ends up being remarkably small. So, and I mean, essentially, we're going to split into 8 children, just some like a little bit of optimization there. And we're, again, assuming that the graph must be much larger than the machine, but each split is going to cost sort of 1 round trip to memory in order to determine these. And so what we're going to pay here is we're going to pay however many nodes we have in the computation times the amount of time it takes to do memory and remote sends, which are on the order of a microsecond, like half a microsecond to a microsecond in the architectures that we've been exploring here, plus a little bit of local stuff within the node, which are on the order of like 1/10 of a microsecond. So for 512 nodes, once all the math works out and we sort of do it, it takes about 26 microseconds to balance a computation across the system, which means that if we want to spend about, like if we have a split of about 2/3, 1/3 for balancing versus compute, we can take something that takes about 50 microseconds per lane and actually load balance that across the graph. And so again, this scales up quite nicely because it's a recursive algorithm, but we are able to just do like load balancing incredibly fast. So next slide. Again, we have a paper on this, but performance is good and roughly linear scaling for this algorithm across lots of different routines. But the slide I know Andrew wants me to get to is the next one on the power efficiency, which is where this thing really sings. So we were comparing it both to sort of standard multi-core nodes, which are this blue strip on the left of these plots, as well as distributed computers, which are the 3 points on the right and this yellow point out here. And so the idea here is that the 2 points in the middle, the teal, so like the green teal with the horizontal stripes, is a single node up-down. And again, we're looking at edges per second per watt for various computations. And so this ends up being the factor of like 5 to 50x for a single node in terms of energy efficiency. But the real win is when we look at these distributed machines, where factors of like 1,000 better than what they're looking like. All right. I think I'm going to skip. Let's see. The next stuff was all on. Yeah, just a summary here. But
so let me skip forward to the.
Yeah.
Oh, did it stop sharing or what happened?
It stopped sharing.
Okay. Let me just skip.
But I think we should skip forward to your summary at this point.
Okay. I'm going to show your up-down performance and context slides.
Okay. Yeah, and then.
Whoops. Where did my Zoom session go? Over there.
There's a question. If you have multiple threads trying to write to the same location, such as your BFS frontier example, how do you protect against collisions? For example, atomic operations, locking, or some other strategy?
I can take that one. So for the frontiers, we have a partitioned frontier. David had to skip over that, but basically each of the active threads is actually writing to a per lane shared per lane shared frontier. So the set of threads actually has a fast local um, uh, uh, monitor or the like on the core, which ensures that only one of them writes at a time. And then you can increment that counter and serialize those writes to the local section of the frontier. The frontier collectively is parallel across millions of lanes. Go ahead, David.
All right. The screen share isn't working for me.
Oh.
Is it?
Not working for me either.
Okay.
Shoot.
Let me share. I can probably do it pretty quickly.
No, I got it here. It's
Oh,
okay.
you got it? Okay.
Yeah.
All right.
Yeah.
Yeah. So just one sort of final slide here. So there's this picture we like to show about up-down performance and context, which is that essentially as you get bigger and bigger graphs, you wind up with these small cliffs. So GPUs are really great. They scale great as long as your graph is small enough. Then if you go over to scale up systems like multi-core, they're a little bit lower performance than GPUs, but you get to much larger graphs. But then if you sort of run out of room in your scale up system, then you get to these scale out systems, distributed computation, where you go off another cliff and you sort of have another order of magnitude lower performance. So we believe that UpDown shows that you can get similar performance across this entire space using this architecture. So you can get higher performance for GPUs locally, as well as absolutely higher performance from these scale out systems. And so this has been realized in a couple of our different projects.
Thanks, David. So, because we're out of time, let me just summarize. So, we believe UpDown enables top-of-stack innovation, both algorithm and data structures, by providing a simple parallelism model and allowing, all kinds of flexible customization and expression of parallelism on top of it. We believe that programming is relatively easy because it doesn't have lots of complicated corners where the hardware, is shaped a certain way and is not controllable by the software. So you can control things you often can't control in other machines, such as memory parallelism, thread scaling, and data movement. And that combined with orthogonal control over compute and data placement gives you low Q properties, right, that enable you to achieve new kinds of data structure and algorithm innovations on this kind of parallel scale-out hardware. So I just wanted to show this slide. We actually today have detailed simulation infrastructure and software tools that enable us to build all these applications and do all these studies. And we published a number of papers about that. I'll just leave you guys with a list of. But the simulations we've done for machines from 2,000 to 1,000,000 lanes on a single node, that a single server, multi-core server can simulate that kind of scale of system. And then scale out simulations on supercomputers to 33 million lanes. We're in the process of building an FPGA prototype of the system. So real soon now we'll have a working FPGA prototype of the hardware. So that's about maturity of the RTL design. And the plan of record is to have ASIC-based systems as early as sometime next year, and then large systems sometime after that. This work is being done at a silicon spinout that we have in Chicago called Chicago UpDown Computing. And longer term, we have a plan to proliferate, prototypes of these systems and so on into the academic community and make large-scale systems available. So we hope to catalyze all kinds of top-of-stack innovation with these kinds of systems. So if you're interested in that, please reach out to us and we'll try and figure out how to incorporate you into such future programs. So with that, we should take whatever time we have left, Bruce, and I'll throw it open to questions. And then there's a whole bunch of papers that I'll just click into the video here so people can see them. So here's one set of papers. Here's another set of papers.
Thank you, Andrew. Thank you, David. We have a couple minutes for questions. There's one already. I'm reminded of work on data flow systems, especially in the use of split phase memory and continuation markers / active messaging. How does this compare or differ from some of these now ancient systems?
Yeah, that's a great question. So I worked on some of those ancient systems. So the connection is real and tangible. I worked on the tag token data flow architecture, and then I was Bill Dalley's first PhD student. So worked on the J machine, which is another event-driven architecture. How does it relate? I think in many ways the mechanisms are inspired by those, but we like to think we've done a better job in a modern context. I would say two things are big differences. The first is that we've taken this message passing model that was in the J machine, event-driven model in the J machine, and active messages, and we fused it with that kind of split transaction memory model, right? So those two things together gives us this really nice unified event-driven model that allow you to manage all kinds of parallelism in the machine kind of uniformly. That's one big important thing. The second thing that we don't spend much time talking about, but is a huge sea change, is the advent of high bandwidth memory has actually transformed the landscape. Because high bandwidth memory is not just high bandwidth, it's super high parallelism. The only way you get the bandwidth out of the memory is to have thousands and thousands of outstanding memory requests, right? So the only way to generate them, right? CPUs are really bad at generating them. GPUs can only generate them in block form, basically, right? We can generate them in irregular, all kinds of unstructured form under software control. So the combination of that cheap memory, parallelism, and bandwidth with these very, very powerful mechanisms that, yes, indeed, go back 35 years, right, or 40, is in some sense the central secret sauce. So thank you for pointing that out. Yeah.
Any other questions before we wrap up?
Yeah, I have a question. So you mentioned like the programmer gets to have a lot of control, like over thread management, things like that. So I guess I'm wondering, like, what is the target programmer here? Do you require the programmer to have like a basic understanding of parallel programming, or or can somebody who hasn't written a parallel program before still use this system?
Yeah, it's a good question. The folks who programmed this system were my graduate students, all a brilliant, hardworking bunch, of course. But they basically had almost no parallel programming background when they started. So I think the answer is at some level, you don't need to know too much detailed parallel programming. Like if you took a graph algorithms class, like you teach, I'm sure, and David teaches, or Charles teaches, and know about abstract concepts like parallelism over vertices and edges, you can program at that level. And then the other piece, the lower level event-driven piece, right? We tell people basically you need to make your events short, right? So they don't block the pipelines, right? And then what they need to understand at that level is sort of the same level as a front-end programmer for JavaScript React. So we don't consider those to be sort of heavy duty, Elvis programmers, right? So I think that it's pretty approachable. Now, the tools are research quality and a little bit raw, you know, those kinds of caveats apply. But I think from a conceptual point of view, we believe this can be a system that's not too difficult to think about programming, and that's by design. Yeah.
Great, thanks.
Thank you. So we're out of time, and really appreciate Andrew and David. Thank you for a great talk. If there's other questions, just to confirm, I assume people can reach out to you and follow up.
Absolutely. We would welcome that. Please do reach out.
Fantastic. And I'll be posting, here comes some applause on the screen. I'll be posting a recording in the next day or two on the Fastcode site. So that brings us to a close. Thank you, everyone. Thanks again to our speakers. We'll see you next time.
Thanks, Bruce. And we have a bunch of papers on our website. And of course, these days, if you ask AI about the UpDown system, you'll find out lots of things about us. Yeah. Thank you.
Great.
Oh, thank you so much.
Bye.
Bye.